In this lecture, gang, what we're going to do is talk about the 7 indeterminate forms. Okay, the 7 indeterminate forms. You'll notice I've got them listed to the left here. One of them you've probably seen already when you were learning limits for the first time in Calculus 1, the indeterminate form of the type 0 divided by 0. But there are others, right? Infinity divided by infinity, or negative infinity divided by positive infinity. It makes no difference, okay? And then we have 0 times infinity, infinity minus infinity, right? Infinity is not even a number, right? It's a suggestion. It suggests to us increases without bound, right? And then we have 0 to the 0 power, infinity to the 0, and 1 to the infinity. In fact, 1 to the infinity, we explored that one a little bit and saw why that would be an indeterminate form in the introduction, our YouTube video, okay? So here's some examples, okay? Okay. Now we know from our experiences that we are allowed to evaluate the limits of elementary functions by direct substitution on their domains. It's just that x, right, the number 2 right here is the number 2 that we would like to substitute into this rational function in the domain. Well, no, it's not, right? In fact, it's a restriction on the denominator. Now, symbolically, gang, symbolically, if you were to do direct substitution, in the numerator, you would have 0, and in the denominator, you would still have 0. Okay, so we say symbolically, the limit of this expression so far is the indeterminate form of the type 0 divided by 0. So how did you solve that? Yeah, good. We got around that, right, by factoring the numerator and canceling common factors. Okay, now at this point, you're just looking at x plus 2, and you're thinking, well, okay, that's a polynomial. I can evaluate this one by direct substitution to get a value of 4. Okay. Now, again, you could graph the rational expression, x squared minus 4 over x minus 2. You could graph it, right? Remember, we learned when we first started out talking about limits back in Calculus 1, we explored their values by using tables and graphs. And you can certainly fall back on those two things too. Sometimes they're not very practical because the graph of a function might be too difficult to draw without a lot of analysis, you know, which would kind of defeat the purpose, I would think. Okay, so here we have the limit as x approaches infinity of the fraction x divided by e to the x, okay? So this is one of those end behavior limits. You remember that from Calculus 1? Now, again, notice in the numerator, you actually have just the identity function, right? Y equals x. Think of the identity function. In the denominator, you have the exponential function. And just to illustrate the point, I know that the identity function looks like this. And the basic exponential function e to the x, well, that just looks like this. So notice, again, look at both of those graphs. As x goes all the way out to the right, notice that both of them increase without bound, right? Both of their graphs rise without bound. So symbolically, you've got one of these things going on. The numerator and the denominator are increasing without bound, symbolically. Right, well, that's one of our 7 indeterminate forms. It doesn't mean that the limit doesn't exist. It just means that further investigation is necessary. Now, you might guess by looking at the graphs to the right that because the red one rises so much more faster, right, so much faster than the blue one does, like if it was a competition, you know, like a race, Looks like the red one's going to win because it increases faster than the blue one does. But gang, notice that the e to the x, the one that's growing faster, is in the denominator. So if the denominator of a fraction is getting bigger and bigger than the numerator to be sure, what do you expect that limit should be? Yeah, you would expect the limit to equal 0. Okay, now that's not proof. Just because we say a thing is so doesn't make it so, right? We would like a little bit more clarification. I will say, however, that those two graphs to the right sure make a pretty compelling geometric argument. Okay, so we have the following, and this will be very helpful for us. This is called L'Hopital's rule. Okay, and gang, L'Hopital's rule says this. If you take the limit of the ratio of two functions, okay, take the ratio of the limit of two functions, and you get back symbolically either 0 over 0 or infinity over infinity. L'Hopital's rule says that you can replace the limit with a new one, and they will be equivalent. And here's what the new one looks like. Okay, now be careful, that's not the quotient rule. Okay, it's simply the derivative of the numerator and the derivative of the denominator. Okay, so this guy was able to show that if a limit led to one of the two indeterminate forms of the type 0 over 0 or infinity over infinity, then you could replace that limit with an equivalent one where you take the derivative of the numerator and the derivative of the denominator. And who cares? Well, gang, it may very well be that that second limit is actually will lead to something that's not an indeterminate form. Okay. All right. Now, some remarks. Notice, gang, I did not put anything underneath of the limit symbols. So you can have, for example, you can have x approaches some number. You can have x approaches some number from the right or the left. You can have one of these or one of these. It makes no difference what x approaches. What matters is that you get either one of these. That's what makes the difference, okay? All right. Oh, you know what, gang, just real quick, let me scroll back up here. Notice that in the infinity over infinity symbol, you can have different signs like this or like this. The signs of the infinity symbols in that configuration, it doesn't matter, okay? It's still an indeterminate form of the type infinity over infinity, okay? Also, down here, you could have a negative infinity plus positive infinity, okay? That's an indeterminate form. However, this is not indeterminate. Minus infinity is exactly what you think it is, minus infinity, okay? Positive infinity plus positive infinity, that's not an indeterminate form. Again, that's exactly what you would expect it to be, positive infinity. It's only when they have opposite signs. You may remember this very special limit, the limit of the sine of x divided by x as x approaches 0, right? This limit is equal to 1. Gang, symbolically, notice that by direct substitution, if you could do it, but you can't, remember, 0 is not in the domain of this function. But symbolically, if you did substitution, you would have the sine of 0 divided by 0, which is this indeterminate form. So that suggests that we can use L'Hopital's rule and replace this limit with a new one. Make a note to myself when I go back and look at this later, I'm using L'Hopital's rule, or LR, and I'm going to replace this limit with an equivalent one where I take the derivative of the numerator, which is the cosine function, and the derivative of the denominator, which is 1. Okay? At this point, simplify. Okay? Now this limit we can actually do by direct substitution. This is equal to the cosine of 0, which is equal to 1, which is what we expected. Okay? Okay. Now this limit, we saw that the numerator was the identity function from pre-calculus. The denominator was the basic exponential function e to the x. Both of them grew without bound, and so led to the indeterminate form infinity over infinity. We guessed by looking at their graphs individually that the numerator or the denominator would grow faster, and so therefore the overall value should approach 0. But because it's an indeterminate form of the type infinity over infinity, I can use L'Hopital's rule and replace this limit with an equivalent one, where we take the derivative of the numerator and the derivative of the denominator, which we know is just itself. There's nothing to simplify here, just take the limit. As x approaches infinity, the denominator will grow without bound. And so therefore the overall value of the fraction will approach 0, again, as we surmised. Let's do this. I got one. Let's do this one. Okay, let's take a look at that again. Sine of x divided by x. So again, what's happening here? The denominator has the identity function in it. Okay, so that's going to grow without bound. But the sine function, all that's going to do is just oscillate back and forth between -1 and +1. So we don't have an indeterminate, we don't have one of those 7 indeterminate forms, as it turns out, in this particular case. So you got to be careful. We might guess as to what the solution is. You want to take a guess? Think about this, right? What's the greatest the numerator could ever be in value, right? It's a sine function. So you got to remember back from your trigonometry days, right? Well, we just said it a moment ago too, right? That the greatest the sine function could ever be is a +1. But the denominator is going to continue to increase without bound. Yeah, it seems reasonable to suggest that this limit is going to approach 0, okay? Now, once again, that's not proof. We're just talking about it. Instead, let's try this. We know that that's true from our trigonometry days, okay? The sine of x is between -1 and +1 inclusive. Now I'm going to divide both sides by x. Now this is legal, right? Ordinarily, you would not want to do something like that, right? We know from our algebra days, you don't multiply or divide an inequality by a variable expression because you don't know when that variable expression is going to be positive or when it's going to be negative, right? And if it's negative, you have to switch the direction of the symbols. But the key to this, kids, is right here. X is going to positive infinity through positive values. And so therefore, we can be sure that over here, we are dividing by positive values of x only, okay? Now take the limit. Okay, so the limit as x approaches infinity of -1 divided by x, well, the numerator is always -1, but the denominator increases without bound. And so therefore, this fraction is going to go to 0. And in a similar way, this fraction is going to go to 0 as well. What we're left with in the middle is this, right? And you've got a less than or equal to symbol and a less than or equal to symbol. The only way algebraically this inequality makes sense is if the number in between is 0 also. Remember, we called that the squeeze theorem. And so therefore, we were right. We made a conjecture, we took a guess, an educated guess that this limit should be 0, but now we actually formally proved it mathematically, okay? All right, what about this? X times the natural logarithm of X. Well, let's see. You've got the identity function multiplied by the basic logarithmic function. Quick sketch of the graph of those two things I'll put right here. Okay, so we have the identity function, which looks like this, right? That's y equals x. That's this right here. And then the basic logarithmic function, well, that looks like this. Okay. Now, mind you, gang, we're approaching the limit says x is approaching 0 from the right-hand side. Well, as we approach 0 from the right-hand side, the identity function itself is approaching 0. But the basic logarithmic function, the closer you get to 0 from the right, the further down it goes without bound. And so symbolically, what we have is this: 0 times a negative infinity. Okay, 0 times a negative infinity. Let me scroll back up and remind you of our 7 indeterminate forms. Okay, we're looking at this one. Okay, the sign of the infinity symbol doesn't matter. It's the type that matters. We have 0 times negative infinity. That's this type right here. Well, we can't use L'Hopital's rule on that. L'Hopital's rule only works on the first two, 0 over 0 and infinity over infinity. So now what are we going to do? Well, I'll show you. Rewrite your limit. Okay, algebraically, rewrite, no L'Hopital's rule, no calculus. Algebraically manipulate the expression. And here's how I'm going to do it. See that x next to the logarithm? I'm going to write it in the denominator like this. Okay, right? The rule for division by a fraction is that you flip it over and multiply. So I flip 1 over x over, and I'm going to get back to the original expression, x ln x. But gang, more to the point now, I've got the basic reciprocal function in the denominator. Do you see that? I have the basic reciprocal function in the denominator. What does 1 over x look like? Well, let's just add that to our picture over here. Why not? Here's what 1 over x looks like. Okay. Now notice, as x approaches 0 from the right-hand side now, the logarithmic function, the red graph, decreases without bound. Okay, so we're looking at negative infinity. The reciprocal function increases without bound, right? The closer you get to the origin, the higher the green graph goes. In the denominator, you've got this. That's an indeterminate form of the type infinity over infinity. Now we can use L'Hopital's rule. So we can now replace this limit with a new one that is equivalent in value, where we take the derivative of the numerator, and we now know that the derivative of the logarithm of x is 1 over x. And the derivative of 1 over x in the denominator is negative 1 over x squared. Okay? Now you have to simplify next. Don't go trying to take the limit. Simplify it. Okay, so flip the bottom fraction over. You have 1 over x times x squared over 1. Cancel one of the common factors. Now this you can do by direct substitution. And so the original limit, gang, right, go back up to this, right? The original limit, we're saying, is equal to 0. But you see how we tackled it? We got the indeterminate form of the type 0 times infinity, and we algebraically manipulated the expression in such a way that we could get an indeterminate form that we could use L'Hopital's rule for, which is 0 over 0 or infinity over infinity. Now, I want to point something out to you, gang, before we leave this problem. Come back to this step right here. Let's suppose that you did not simplify before you attempted the limit. Okay, suppose you did not simplify and you just attempted the limit right now. Well, if you did, this is what you would get. In the numerator, you would get symbolically positive infinity. In the denominator, you would get symbolically negative infinity. And that's a correct form for L'Hopital's rule. And so you would use L'Hopital's rule again, right? You would actually use L'Hopital's rule on this expression here. And here's what you would get. Okay? So you attempt the limit again, and if you do, you're going to get infinity over infinity, and it's just going to keep going and keep going and keep going, okay? So remember this, okay? Whenever you apply L'Hopital's rule, make sure that you simplify right after, okay? You don't want to use L'Hopital's rule where you're not allowed to, and this is one of those instances, okay? So let me say it again. After you apply L'Hopital's rule, you must simplify before you attempt the next limit. Okay, so let's go back up to our list and let's make a note. If you get an indeterminate form of one of these two types, the idea is to use algebra or trigonometry, whatever, to manipulate the expression in such a way that you get either 0 over 0 or infinity over infinity. Remember, again, the idea behind indeterminate forms is to be able to use L'Hopital's rule, okay? All right, but what about these three? These, gang, I refer to these as exponential type. These are exponential type. Okay, they're the least desirable of the 7 because they usually require a little bit more work. Okay, let me show you what happens when you get one of these. Okay, now we saw in the introduction what this would lead to ultimately, right? But if you forgot, that's good. Maybe you'll be surprised, right? Now, symbolically, what's happening here is that on the inside of the parentheses, the 1 plus 1 over x, right? The fraction 1 over x is going to 0, right? As x grows without bound, that fraction goes to 0. So symbolically, you're going to have this expression, 1 on the inside, and the exponent is going to infinity, all right? So that's one of the 3 exponential types, all right? So it's an indeterminate form. So what to do about it? First of all, is to recognize what's causing the problem. The problem is the exponent, okay? Not the 1. The 1's in parentheses, it's fine. It's the exponent that's causing the problem. From your experiences, gang, how do you get an exponent out of the exponent? Good, you use logarithms. Yes, and that's what we're going to do. Now, I'm going to create an equation. And I'm going to assume the limit exists, okay? Because we don't know what's going to happen. An indeterminate form doesn't mean the limit doesn't exist. Doesn't mean it does exist either. It just means further investigation is necessary. So let's assume the limit exists and let's give it a name. Let's call it L. L for limit, because, you know, that's original. Okay, now the reason that I'm creating an equation like this, okay, because that's what it does. Okay, as soon as you give the limit a name like this, you create an equation, and now you have an equation for which you can do this. Okay, so you just can't slap a logarithm in front of an expression. We have to obey the rules of algebra. We can't defy the rules of algebra. Right. So what I did was I was clever. I created an, and I wish I could say it was my idea. I'm just saying I'm being clever, but it's a clever idea. But what we did is we called it a name. We called it L, which creates an equation for which we can then take the logarithm of both sides. All right. So where's this going to go? Well, from your work in your Calculus 1 days, gang, when you studied limits, you know that you can switch the function symbol and the limit symbol as long as, oops, the function is continuous. And as x goes to infinity, it certainly will be. 1 plus 1 over x to the x is discontinuous where x is equal to 0. But in our case, x is going to infinity. We're nowhere near the origin, okay? So what we're doing is legal. Okay? All right, now I'll bring that power down in front, right? That's one of the 3 properties of logarithms from the old days, huh? Okay, so what was causing the problem at the beginning? It was the exponent. Now we took the logarithm of both sides of an equation that we created. We got that exponent out of the exponent, and it's no longer a problem anymore. So let's try the limit, okay? Stands to reason. All right, let's see. Let's see what's happening symbolically, okay? All right, x is going to infinity, to be sure, right? That says so here. So this x, increasing without bound. What about the logarithm? Well, notice that the argument, again, notice the argument of the logarithm, 1 plus 1 over x, right? As x increases without bound, right? X goes to infinity. 1 over x goes to 0. And so this whole expression here is going to 1. But the logarithm of 1 is equal to 0. Well, look at that. We have another indeterminate form. But this indeterminate form is better than the last one. It's kind of like, let me scroll back up so you can see this. This is so cool. God, it's good to be us. Look at this. We started down here. We just worked our way up. It's like we're working our way up the ladder. Okay? Now we have an indeterminate form of the type 0 times infinity. And what do we do when we get either one of these two? We use algebra to manipulate the expression so that we can get back to one of those and be able to use L'Hopital's rule. Okay. So I'm going to do like we did in a previous example. That x that you see out front, I'm going to write it in the denominator as 1 over x, okay? Right, that's algebraically equivalent. X in the numerator is equivalent to 1 over x in the denominator, okay? Now symbolically, what will you have? Well, symbolically, you're going to, as x increases without bound right here, you're going to get the logarithm of 1, which is 0. And in the denominator, the reciprocal function also goes to 0. Yes. Now we've got the correct indeterminate form. Now we can use L'Hopital's rule. Okay. So I'm going to replace this limit right here with a new one where I take the derivative of the numerator and the derivative of the denominator. All right, so the derivative of the numerator, the derivative of the logarithm of 1 plus 1 over x is 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x. In the denominator, the derivative of the reciprocal function is negative 1 over x squared. Next, we simplify. Notice we can cancel common factors. And if you attempt the limit now, notice in the denominator will go to 1. Okay, now you're not finished, be careful. The logarithm of your limit is equal to 1. You need to know what the value of the limit itself is, okay? So if ln of our limit is equal to 1, this implies that the limit, L, is equal to e to the 1. Okay, now, oh my goodness, a lot has happened, right? What does L equal? Scroll back up here. Remember, L was the name that we gave to our limit. All right, so let's go down here for completeness. Let's switch this out. So when we go back and look at this later, we know what we were thinking. That L is the limit as x goes to infinity, 1 plus 1 over x to the x power. Okay. And we actually refer to that, gang, as a definition for the natural number e. Okay, so that's how you tackle the indeterminate forms of the exponential type.